Welcome back to the course in Nuclear Medicine Physics. Today is an introduction to kinetic modeling of radio tracers in the body. The ultimate goal here is as follows. You inject somebody with a radio tracer and it moves throughout their body. But that activity isn't constant as a function of time, it changes. And what you want to do is you want to model the change in the radio tracer in different regions of the body as a function of time. This video will focus mainly on establishing the mathematical formalism of how we model radio tracer kinetics in the body. A given model will give specific differential equations, which, when solved, will give you an estimate for what the radio tracer concentration looks like as a function of time. In the end, these different models that we come up with can be compared to real data to validate the models and get an idea of what's the best description of what's actually happening in the body. Anyways, enjoy.
All right, so it's a real pleasure to be talking about the all-important topic of kinetic modeling as applied to nuclear medicine. Historically, this has been more commonly applied to PET imaging, but also it is applicable to SPECT imaging, for example. And similar frameworks can be and have been applied in other fields, such as in perfusion MRI, dynamic contrast enhanced MRI, and the likes. So I want to first acknowledge that I have benefited from a number of slides from colleagues, Dr. Vezensasi, Dr. Minzao, and there's a very valuable course that's been offered over the years, a short course on kinetic modeling by different colleagues, and I've benefited from slides from Drs. Rich Carson, Roger Gunn, Adrian Lemertzma, Julie Price, and Jörg van den Hoff. Okay, so the driving question is, how do we relate quantitative images? Let's say you have a set of dynamic PET images in units of, let's say, kilobecquerels per cc or becquerels per cc. How do we relate these actual images to physiologically meaningful parameters like blood flow or receptor binding or metabolism, rate of metabolism? And one common answer has been to use kinetic modeling techniques, commonly coupled with dynamic imaging. So as we have emphasized in the past, the standard optic value, which is very commonly used, is considered relatively semi-quantitative compared to kinetic modeling-based measures. And in fact, historically, kinetic modeling methods have been used as a gold standard to verify that SUV methods are somewhat similar or related, or do a good job of approximating in certain applications. So modeling is a tool to quantitatively compare the strength of specific processes, as we will see, for example, some examples, and is also a data reduction method. So imagine that you have many images and many slices over time. So clearly here we're dealing with a lot of data. How do we extract meaningful and manageable information, right? So again, I want to summarize that large information into tractable and functional information that allows us to better distinguish between, let's say, normal patients and, let's say, a particular kind of disease, like, let's say, Parkinson's disease in this example. So again, we're looking for quantitative parameters that allow us to extract images or extracted from images that allow differentiation of normal versus abnormal conditions. So for example, if we were to do that between normals and Parkinson's disease, hopefully that would allow us to distinguish between patients. So I kind of like to think of kinetic modeling as, though nobody really calls it that way, but I like to think of it as a reconstruction problem. So we have another kind of reconstruction that we're all accustomed to, and that's image reconstruction, where you have the measured data on a, let's say, tomographic scanner, and the input is, the radio pharmaceutical distribution in the body, and there's a system which is the scanner, let's say the PET scanner, And the more we understand about the PET system, the scanner system, the physics of it, and once we have measured the data, we could do an image reconstruction. It's a nice, interesting inverse problem to reconstruct the images. So here's the systems defined by physics, but there's a whole different reconstruction problem where the system's not the scanner, but it's the subject physiology, let's say the human body. So there's something that goes into the human body, and that is, for example, think of as radiopharmaceutical distribution in the blood. So kind of like the input that goes into the body, and the output is how that radiopharmaceutical distributes in tissue over time. So we are measuring this. In fact, these are the dynamic images that we have reconstructed in this problem. So we have measured these now. And let's say we have a way of measuring the distribution of the radiopharmaceutical over time in the blood, in the plasma. So we have this and we have this, and from those we reconstruct or estimate certain parameters, certain, let's say, microparameters in the subject physiology. So here, definition of the systems based on mathematical biology. So imagine that we measure a time course of a radiopharmaceutical, a radio tracer, by performing a temporal sequence of scans. In this case, brain imaging. You put a region of interest over a certain region, let's say in the caudate or the putamen in the brain. You track how the average uptake in that region of interest changes over time. So you're observing a process here. A time activity curve is being generated. And again, let's assume that we have measured, let's say by blood sampling over time, now this sounds invasive, right? Like you were saying, are you really going to do blood sampling? Now the answer is, in some kinetic models, you have to do that, but in some kinetic models, you can actually use a reference region in the body that does the job of, or a blood pool in the body, or some reference region in the body that does the job, and you don't have to do invasive plasma input function sampling. But let's say we have this measured and you have this measured, and of course the assumption here is that these are quantitative information. We've talked extensively in the past about how to create quantitative images. Once everything is reliable and quantitative, from that, using mathematical biology, you might be able to estimate the system parameters. So the goal is to parameterize the process of interest using mathematical biological models. The model requires math, which determines the model, the parameters, and some biology that interprets the meaning and provides interpretation of the meaning of the parameters, and some kind of assumptions, right? So I like this quotation: mathematical modeling is the art of judicious oversimplification. We're always simplifying or oversimplifying, but hopefully it's judicious and we understand the trade-offs in accuracy and precision, which I will also try to talk about. So the choice of the model depends on the process, the particular radiopharmaceutical that is being used, the amount of information that we want to extract, whether we want to extract, specific microparameters, or maybe we want to estimate a combination of the microparameters, like a macro parameter that combines a few microparameters, and the complexity of the scanning protocol. So compartmental models have really been used in a number of fields that you can, for example, see listed here. I'm sure you've seen these kind of models, writing ordinary differential equations, ODEs, to estimate certain parameters. But let's talk in this specific context. So what's a compartment? So a compartment is like a volume or space within which the tracer behaves kinetically in a homogeneous manner. Okay, so this could be a physical distinction, like physically distinct compartment, like a blood pool versus the myocardium. Okay, but it could also be, they could be nearly at the same location, but the distinction is chemical, not physical. So whether the radiopharmaceutical is in a free format or it has been metabolized. Okay. So free form versus metabolized. And again, the definition of compartment is radiopharmaceutical and radiotracer dependent and can be reversible. So once the tracer of interest enters a certain compartment, it can leave, or irreversible. Once you enter, you cannot leave the compound. Okay, so here are examples of different compartmental models. You may see two compartments here, but we actually call this one tissue compartment. Typically, these have been written for brain imaging applications, and they've been translated to other parts. So sometimes when you see this line, this means the blood-brain barrier, which you really don't have to draw, because in many applications, it's not about the brain. So you don't have this blood-brain barrier. But this is the plasma. So this is a distribution of the radiopharmaceutical in the blood, in the plasma. And this would be when it enters tissue. So this is why we call this a one tissue compartment. Even though there are two compartments, we call this one tissue compartment. This is a two tissue compartment, though it has three compartments, three tissue compartment. And as you can sort of see, as you add a new compartment, you tend to gain two extra parameters: the rate by which you enter that compartment, the rate by which you leave that compartment. So the model can become increasingly complicated. So just to use some terminology here, so this is the input function, the plasma input function CP. These are the rate constants, which we also call the kinetic microparameters, K1 and K2. And this is the tissue compartment, right? And what you observe tends to be what's in the tissue, but there might be a little presence. This is why we have a partial, a box partially overlapping this plasma input function, because in the tissue of interest, you may have blood present, okay? So for example, if you're focusing on a certain region in the brain, people tend to assume, let's say 3-4% of that there's blood, presence of blood. In the heart, there's a much higher presence. So if you're, for example, putting a region of interest in the myocardium, you can assume that there's blood in the myocardium. Also, there's spill out from the blood pool because of the limited spatial resolution into the myocardium. So that fraction tends to be much higher. But the point is, typically what you measure is the tissue, how much is the radiopharmaceutical in the tissue plus a little bit of the plasma. And that could be a parameter that you estimate what fraction that is. But sometimes people don't write that. Sometimes they just sort of approximate the region of interest as being composed of only the tissue component and not any plasma, and any blood. So again, looking at certain rates and rate constants that you see listed here, and different kind of models. This is one tissue compartment. One tissue, I should really be saying one tissue compartment, because technically it's really two compartments. One tissue compartment, two tissue compartment. So here you're adding, more parameters. Is K1 only if it's irreversible, but it's K1 and K2 if it's reversible. Here, if it's K1, K2, K3, if it's irreversible two tissue compartment, here's we've got 4 parameters if it's reversible two tissue compartment. And you may see these other things listed. Okay, so this is Ki. Okay, so this is Ki here. Ki, as we will see later, is a combination of these 3 parameters. So K1, K2, K3 are microparameters, but Ki, which is a combination of these 3 parameters, we call it's a macro parameter. And sometimes in a certain estimation task, which I'll talk about in the next lecture, we don't estimate these individually, we estimate the combination of these terms. And then there's this volume of distribution, or distribution volume, which is another term. So you can sort of see certain expressions. I won't go through the details, but for example, in a 2-tissue compartment model, which is common in receptor ligand modeling in brain applications, the ratio of K3 over K4 is a very important parameter. It's a macro parameter because it's a combination of micro parameters. So this K3 over K4 is a parameter of interest. Of course, it's best to estimate K3 and K4 separately, but in certain parameter estimation methods, it's more robust to estimate this ratio. And this ratio is referred to as a binding potential, okay, in receptor ligand modeling. And also, when you go through some of the math, you'll see that once you reach equilibrium in these systems, the ratio of the tissue compartment, so this plus that, over the plasma, when you reach equilibrium, so when this derivative is equal to 0, that ratio is referred to as the distribution volume, okay? So you can see a term for that. Distribution volume turns out to be given by this expression. So you may see a lot of people referring to binding potential or the distribution volume or volume of distribution, and you'll see that these parameters are what they mean. And again, these are macro parameters. So going back to here, you sort of see this macro parameter, also Ki, and a macro parameter. But here you have a micro parameter, so K1. You may also want to estimate K2 or K3, But for example, in cardiac imaging, as you will see shortly, people really care about K1. Okay. So moving on. So again, looking at the blood-brain barrier line here, again, which historically is drawn, but again, these models are equally applicable to non-brain applications. So you can mathematically write the ODEs, the ordinary differential equations here, which are with respect to time, and then you can estimate these parameters. So this is just a visual drawing of a receptor ligand model where you've got the plasma activity, so the radiopharmaceutical in the blood, penetrating the blood-brain barrier with the rate of K1, but going back to it with the rate of K2. It's free, and then it gets bound, for example, to a receptors in the brain. Let's say the D2 receptors. Okay, so you're studying dopamine and what that means, or you're doing a study on addiction, and you want to study what happens, for example, right? In the case of a stimulant or stimulus. Okay, so how do we actually estimate these parameters? Let's say, how do we estimate K1? How do we estimate K2, right? So there are different approaches. So I want to first say that you could estimate these parameters, these, for example, micro parameters, K1, K2, K3, K4 at the region of interest basis. So you would be drawing a region of interest over a certain area that you care about and you want to study. Or you could do this for every single pixel or voxel, right? So here you would only be getting kinetic parameters for a certain region of interest, whereas here you are actually estimating that for every single voxel. And so there's pros and cons to this, right? So the advantage of this is that it's less sensitive to noise because you're averaging across a region of interest before you do kinetic parameter estimation. So there are advantages of that, and which region you're focusing on, so that model, it should work for that. You have more control over it. Disadvantage is that you're pre-selecting. But when you do parametric imaging or parameter estimation at the pixel or voxel level, you are not pre-selecting any region. Of course, it's going to make it more computationally intense. That's okay, but it's also going to be very sensitive to noise, right? So you have to be careful about that. So this field of parametric imaging is an exciting field, and it requires a lot of attention. So here's an example where you've got, let's say, a PET scan. I'm just showing you one image, but this would be over time. And then you apply a certain model, and then you estimate a certain parameter, let's say K1 or K2 or K3 over K4, which is a binding potential, and you show that image, right? So this is a parametric image. It's a functional image. So this is an image where each pixel, each voxel value has physiological meaning. So here's just examples. During my time at Johns Hopkins University, we would be studying, and we continue to study, many sites continue to study many different receptors, for example. So for example, dopamine. So you got different, raclopride, for example, which is a radiopharmaceutical, looking at dopamine receptors, methylphenidate, looking at dopamine transporters, and a whole range of things, looking at serotonin, looking at norepinephrine, and you got mu-opioid receptors, you got cannabinoid, and things like that. And these are parametric images, though they have been averaged over multiple patients, all registered to the same space, just to show you the feel that these kind of parametric images, some of them could be a parametric image of binding potential, some could be distribution volume. The point is that parametric imaging can be quite powerful. So we wrote this in 2020. There was a special issue, but we wrote this sort of editorial, but it's really a review of the field PET parametric imaging, so you may check it out. So PET parametric imaging has definitely picked up pace over the years, but there are challenges associated with it. There are potentials for it, so you could check that out. And here we in one of the tables there, we listed a lot of software packages that are out there that allow you to do kinetic modeling, and a fraction of those that we list here, in fact, the majority of them also allow you to do parametric imaging, meaning doing the kinetic modeling at the individual pixel voxel level, or at sub-regions at least, right? So you can check these out, and whether they're commercial or freely available. So there's a lot of resources out there. And so the question is, okay, again, how do we estimate these microparameters? And again, the models could become increasingly complex as you add For example, here you're having a K1 and K2, but then you also have K3 and K4 for specific binding. But you may also be binding, so K3, K4, sorry, here for specific binding, but you may also be binding to things that you don't care about. So maybe a K5 and a K6, and that complicates things, right? So we need to judiciously oversimplify our models, right? So again, you're having this is a free tracer. It is here bound to the thing you're really trying to study, to the receptor you care about, you want to study, but it may also non-specifically bind to receptors, for example, that you don't care about, but it just happens to be there. So these are the observables, the total uptake in the tissue, the uptake in the blood. But again, the models could become very complicated. So people tend to, what if you also have tracer metabolites? Now you've got even more compartments, and that's a big headache given the data that we have, right? So people tend to oversimplify things or simplify things, right? So this, you may arrive at this, you may, design radiopharmaceuticals that do not have significant metabolites. And then you may arrive at this. This is again non-specific binding, but you may sort of assume that you quickly equilibrate between these two. So you further oversimplify. So if I want to really summarize everything, this tends to be a pretty common model, two-tissue compartmental model, right? And this is a reversible version of it, but you could also have an irreversible version where the K4 is essentially negligible, okay? So for FDG, we would do that. So again, you have to identify the most relevant parameters, make certain assumptions, and start estimating. So this is a model of two-tissue compartment, K1, K2, K3, irreversible. So you may want to estimate K3 or a combination of all of these. And here's a reversible model where you may want to estimate K3 or K4 or a ratio of the two, a macro parameter. So I keep iterating the same thing, but I just want to sort of emphasize that. So how do we estimate these? Well, there are different approaches. A common approach has been to basically to do nonlinear fits to the time activity curves. So compartmental model approach, nonlinear fitting, right? So, you may have these different models, and you may apply, you could solve these differential ODEs or ordinary differential equations. You could solve them different ways using Laplace transforms or different methods. For example, this one tissue compartment, you could solve, you arrive at this formula. I'm not gonna, focus on the formulas, right? I mean, you can sort of refer to them and work them out if you're further interested. But so this is the actual solution, for example, for this model. This is a solution for this model, for the two-tissue irreversible model, right? So you have these, now you have solutions for them, and you basically fit them, right? So what K1, K2, and K3 allows you to fit the data. So you may do least squares fitting, which is common, and you should be inspecting the residuals. So because if a fit is kind of not doing a good job of fitting, you'll see that the residuals here might be on one side and the residuals here might be on the other side. So that actually means that the model itself is not good enough. You're not able to fit the data well, because when you look at the residuals, there's one side being more negative, one side being more positive. Here's another example where you're having the blue dots are the actual measured data. And if you use a one tissue compartmental model to fit it, you just can't fit it. And of course, if you had, this is obvious, so you don't even need to look at the residuals, but obviously the residuals here would be, positive errors, negative errors, you would totally see it. But here's a two tissue compartmental model. So this is when people are trying to figure out, which model is the best to fit this data, right? So there's a lot of inspection going on. And so the two tissue compartmental model does a good job of fitting. And then the question is, okay, so we're estimating using nonlinear fitting these micro parameters, K1, K2, K3, and maybe K4 if it's reversible. But are there other approaches to kinetic parameter estimation that can be used? And the answer is yes. And we're going to talk about that next.